So in the ideally joined chain, the ideal chain model or the freely joined chain model, we make some pretty extreme, actually some very radical, I think, assumptions. So we are going to assume that there are no intermolecular or steric interactions, and basically I can put, you know, monomers and have them cross each other without any penalty. So we're ignoring essentially bond angle restrictions, we're ignoring interactions, and we're just kind of randomly placing a polymer or monomer unit anywhere, kind of what you see here. So this is quite, really not physical if you if you think about it, and it's completely random. Essentially, they are completely uncorrelated. So we can actually derive the our r squared mean or root mean squared end-to-end distance of our polymer chain with these assumptions built in. So if I look at this ideally joined chain model, my r is simply going to be the sum of all of those monomer units, L sub I. So that would be how I would calculate it. Now, on average, and we can kind of think of this in 1D, perhaps, if I place my monomer unit, I can have it in the positive direction or in the negative direction. And I could flip back and forth and just randomly generate right, left, right, left, right, left steps. So on average, what would be the value of R? On average, it would be 0. But we're trying to calculate our root mean squared end-to-end distance. So if we have R squared, we can write this as the dot product of these vectors. So if I look at this, L1 dot with L1, that's just going to be equal to the magnitude of that, so L squared. What's the angle between basically myself and myself? That's going to be cosine of 0 degrees, and that will be equal to 1. Excellent. So, again, they're going to be pointing in the same direction. So that'll be my value. Now, if I look at the next step, the magnitude of L will still be the same, but, well, it could be pointing in the opposite direction, right? Or it could be pointing in the 0 direction. So I have a probability it could either be +1 or it could be -1. So on average, all of these values will average out. Everything that's not along this diagonal will average out to be 0. So you can extend this and say that these are the only guarantees. This could be +1, this could be -1, they're all going to average out. So on average, that's just going to be 1, 2, all the way to n number of rows. So my root mean squared end-to-end, or root mean squared distance here will be nl squared, and then to the 1/2 power, it's going to be n to the 1/2 L. This freely joined chain model is shockingly accurate for many situations, but specifically for polymers that are in the melt, meaning where there's no solvent. This model actually captures the behavior quite well. Additionally, we see this kind of makes sense. This was our distance for the fully elongated chain. It's scaled as n to the L. The n scaling here is the critical parameter. L is just kind of like a prefactor. So here it's linear, but here we're to the 1/2 power, which makes sense because if I'm letting the polymer kind of just randomly, exist, that's going to be quite smaller than when I force it to fully elongate. So that makes sense, at least conceptually. So we'll see, but we made some kind of critical, again, where's the solvent interaction? What about bond angles? What about bond rotations? Well, luckily, some chemists and some people named Flory will help us out with that later on. So we'll see you in the next video. Thanks. Bye.